Hey fellow nerds, today we are going to discuss some key parameters of BJT amplifiers. We will be covering voltage gain, current gain, input impedance and output impedance. Let us start with voltage and current gain. Assume we have an amplifier. We are giving an input V input. We get an output V output. Obviously, since this is the output of an amplifier, it is going to be a magnified version of the input. We can take the ratio of the output voltage to the input voltage and call it AV. AV will be our voltage gain. We have the input current over here and output current over here. We can even take the ratio of the output current to the input current and call it AI. AI will be our current gain. Now, one question that comes to my mind is this. We have already defined the current gain. Beta, we took it as the ratio of IC to IB and we called it the current gain. So, what is the difference here? It is true that beta is the ratio of the output current to the input current when the transistor is operating in its forward active region. But when we actually make an amplifier circuit, there will be external elements added to it. So we'll get a new input current and a new output current. Current gain of the amplifier AI is the ratio of output current to the input current in the whole circuit. Beta, on the other hand, is simply the ratio of IC by IB, and we call it the intrinsic gain of the transistor that we are using. Let us now take the input and output impedances of an amplifier. First, I will take an ideal voltage amplifier. I am giving an input V input and I am getting an output V output. First of all, we have to get an idea on what the amplifier is doing on the input side and on the output side. V input is provided by some other circuit. So on the input side, the amplifier has to sense some voltage that is given to it. What do we call a device that senses voltage? We call it a voltmeter. So we could say on the input side, the amplifier is acting as a voltmeter. Now, what is it doing on the output side? Here, it is providing some voltage to another circuit. So we can say on the output side, the amplifier is acting as a voltage source. Let's take a resistor. Assume it has some current I flowing through it. Now, if I want to measure or sense the voltage across the resistor, I'll have to connect a voltmeter in parallel to it, like this. Obviously, since now the voltmeter is in the circuit, some of the current will have to flow in this direction. But I don't want that to happen. Because in that case, the current through the resistor R will decrease, voltage across the resistor R will also decrease. I do not want connecting a measuring instrument alter my actual circuit. So what I do is I make sure the resistance of my voltmeter is really high that very less current flow through this. That means the current that flows through R will still be very close to I and my voltmeter will give me a really good measurement of how much is the potential across R. So for an ideal voltmeter, we should have a resistance that is infinite so that no current will flow in this direction. All of the current will flow through R and I will get the most accurate result. When it comes to our amplifier, we saw on the input side it has to work as a voltmeter, which means ideally it should have infinite input impedance. Again, over here we have a cell which is a voltage source. Assume it has some internal resistance R. Obviously, if I want my voltage source to be perfect, all of the voltage V should drop across my resistance R over here. But if the source has an internal resistance, some of the voltage will be dropped across the internal resistance and my resistor R will not get the entire voltage provided V. So ideally the resistance of the voltage source should be 0 so that the entire voltage provided will be dropped across my resistor. When it comes to our amplifier, on the output side it is acting as a voltage source. So ideally it should have 0 output impedance. Now, practically, it is not possible for us to have infinite input impedance and 0 output impedance, but we will try to make sure the input impedance is the highest possible and output impedance is the lowest possible. Let us solve a problem. We have an amplifier whose voltage gain is 10. Whatever is the input, output is going to be 10 times of that. Input is a mic, which basically gives a sinusoidal input. The mic also has its own resistance Rm. It is equal to 200 ohm. Output is a speaker, which we can model as a resistance Rs. It is equal to 8 ohm. We have to determine the input signal that is sensed by the amplifier if the input impedance of the amplifier is 500 ohm and if it is 2 kilo ohm. So our analysis is going to be on the input side. First, let's have a better idea of the circuit. I will take my amplifier. I have also marked its input impedance. It is Rin. Now, this is how we model the mic. We have to connect it across these 2 points like this. There is a resistor Rm, there is a resistance Rin. Rm is the resistance of the mic, Rin is the input impedance of the amplifier. Vm is our actual input, but some of it will be dropped across Rm itself. Whatever is dropped across our input will be sensed by our amplifier. And that will be equal to R input divided by Rm plus Rin multiplied by Vm. It is just a voltage divider. Let us take the first case where R input is 500 ohm. We already know Rm is 200 ohm. Let us substitute our values in this equation. This is what we get. V, or the voltage that is seen across our input, is 500 divided by 200 plus 500 multiplied by Vm. That is equal to 0.7 times Vm. The actual input is Vm, but what is sensed by the amplifier is 71% of it. Let's take the second case where our input is 2 kilo ohm. Again, let us substitute it in the equation. Voltage seen across our input is 2000 divided by 200 plus 2000 multiplied by Vm. This is equal to 0.91 Vm. The actual input is Vm. What the amplifier senses is 91% of it. Obviously, it is better when the input impedance is higher. So we can affirm that the input impedance of the amplifier should be maximum. Let's go to the next part of this problem. Here we have to determine the signal that is delivered to the speaker if the output impedance of the amplifier is 10 ohm and if it is 2 ohm. So here the analysis is to be done on the output. First, let us have a better view of the circuit. I will take my amplifier. On the output side, it is acting as a voltage source. It is acting as a voltage source and it itself has an impedance R out. Exactly like how we modeled our mic. Now, the output of the amplifier is to be connected to the load, which is our speaker. Let us do it. The question is to find how much is the signal delivered to the speaker. So basically, we have to find out how much is the voltage dropped across the speaker, which is modeled as Rs in this circuit. Again, this is a pure voltage divider. Voltage dropped across Rs is going to be Rs divided by R out plus Rs multiplied by V out. V out is whatever we get over here. Let's take the first case where R output is 10 ohm. We already have the value of Rs, it is 8 ohm. Let us substitute the values in this equation. This is what we get. Voltage delivered to the speaker is 8 divided by 10 plus 8 multiplied by the original output. That is 0.44 V output, just 44% of whatever we get over here. Let's try the next case. Our output is 2 ohm. In that case, voltage delivered to the speaker will be 2 divided by 10 plus 2 times V output. That is 0.8 V output. We get 80% of the original signal. Obviously, it is better when the output impedance is lesser. So we can affirm that output impedance should be minimum. Now that it is clear what we are expecting, a high input impedance and a low output impedance, we have to take our amplifier circuit and calculate its input impedance and output impedance. But before that, we have to equip ourselves with something called Thevenin's theorem. Thevenin's theorem helps us model any circuit with just a single voltage source and a single resistor in series with it. Let us see how this can be done. I'll take case 1 when the circuit does not have any dependent sources. Let us take an example. This is my circuit. Here we have a voltage source. Here we have a current source. They are both independent. We have a 4 ohm resistor, a 12 ohm resistor, and a 1 ohm resistor. Using Thevenin's theorem, we can model the same circuit like this: a single voltage source and a single resistance that is in series to it. We'll call these VTH and RTH for Thevenin voltage and Thevenin resistance. To find the Thevenin resistance, there is only one rule: turn off all the independent sources. Over here, we have two independent sources: the voltage source of 32 volt, the current source of 2 ampere. If we turn them off, the circuit will look like this. To turn the voltage source off, I shorted it. To turn the current source off, I opened the circuit over there. Why? When we say turn the voltage source off, that means the voltage there should become 0. Voltage between these 2 points will become 0 if I short them. When we say turn off a current source, we mean the current should become 0. If I short here, obviously the current will not become 0. Current will flow here. So to make the current flowing through that branch 0, I have to open it. Now 0 current will flow through it. So whenever you have to turn off a voltage source, short it. Whenever you have to turn off a current source, open it. Now Thevenin resistance will be the resistance that you see when you look from here. We have a 4 ohm and a 12 ohm in parallel. Also, there is a 1 ohm in series to them. So the Thevenin resistance is simply 4 being parallel to 12 and 1 being in series to them. That gives us 4 ohm. Obviously, we will be using Thevenin's theorem to find the input and output impedances only. So V Thevenin is not important here. But anyways, let's do it for the drill. V Thevenin will be whatever is the voltage that we get over here at the output when the load resistance is not connected. Let's try to find it. Since load resistance is not to be connected, between these 2 points, the circuit is going to be open. That means no current can flow through here. That means through the 1 ohm resistor, no current will be flowing. No potential will drop across it. So even if you remove the 1 ohm resistor, our circuit is going to be exactly the same. To make the circuit simple, let us do that. Now, Thevenin voltage is whatever is the voltage that we get across this current source, or whatever is the voltage that we get across the 12 ohm resistor. Let us assume that this point has 0 potential, and with respect to that, this point has V potential. V Thevenin is obviously the potential difference between this point and this point. Potential at this point is V, potential at this point is 0. So the potential difference between these 2 points is V minus 0 or V. So basically what we have to find out is just the value of V. Let us apply KCL at this node. How many currents will be there? A current will flow through this resistor like this. Current will flow through this resistor like this. There is a 2 ampere that is coming in this direction, and that is all. If you take a look at 4 ohm resistor, it has V potential here and 32 volt here. So the current through it is going to be V minus 32 divided by 4. Potential difference divided by the resistance. For the 12 ohm, it has V potential here and 0 potential here. So the current through it is going to be V minus 0 divided by 12 or V by 12. There is one more current. It is provided by the current source 2 ampere. It is coming into the node. So I will take it as minus 2. According to Kirchhoff's current law, the net current at a node is going to be 0. From this equation, we can easily find out what is the value of V. Simplifying the equation, we get V is 30 volt. That means the Thevenin voltage is 30 volt. Now, we can model this entire complicated circuit like this. A 30 volt source and a 4 ohm resistor in series to it. Now, this was simple because we did not have any dependent sources in the circuit. Let us take the second case where the network has dependent sources. For example, this one. It is almost the same circuit, but there is a slight difference. I have called whatever is the voltage that will be dropped across the 12 ohm as V0. And the current source now has a value 2V0. So the current that is provided by the current source depends on whatever is the voltage that drops across 12 ohm. It is a dependent source. Using Thevenin's theorem, we can model this circuit using just a voltage source and a resistor in series to it. Let us see how it can be done. To find the Thevenin resistance, these are the rules. First of all, turn off all the independent sources. If it is a voltage source, short it. If it is a current source, open it. Second rule is apply a voltage source Vx and determine the resultant Ix. Then Vx divided by Ix will be your Thevenin resistance. Let us see how this can be done. First, I will turn off the independent sources. Then the circuit will look like this. I shorted the 32 volt voltage source over here, but the current source is still here. Why? Because it is not independent. It is dependent on whatever voltage we get over the 12 ohm. Now, the second step is apply a voltage source Vx and determine the resultant Ix. Here we want to find out the Thevenin resistance when we look from here. That means we have to connect a potential Vx across these 2 points. Like this. Now, because of Vx, some current will flow in the circuit in this direction over here. Let us call it Ix. Let us do the same trick we did earlier. I'll take the potential of this point as 0 and this point as V0. It works because we have already taken the potential across 12 ohm to be V0. So we can take 0 here and V0 here, which aligns with the condition that the potential difference across 12 ohm will be V0 minus 0, which is equal to V0. Let us again apply Kirchhoff's current law at this node. How many currents are there? We have a current flowing through the 4 ohm resistor like this. We have a current flowing through the 12 ohm resistor like this. We have the current provided by the dependent current source like this. We also have Ix flowing through the 1 ohm resistor. Now, for the 4 ohm resistor, it has V0 potential here, 0 potential here. Current through it is going to be V0 minus 0 divided by 4 or V0 by 4. For the 12 ohm resistor, it has V0 here, 0 here. Basically, it has a V0 potential across it. So the current flowing through it will be V0 divided by 12. We also have the 2 V0 provided by the dependent current source. Now, we have taken the direction of Ix to be into the node. So Ix will be Vx minus V0 divided by 1. Since it is coming into the node, I will take it as negative. According to Kirchhoff's current law, the net current has to be equal to 0. If we simplify this equation, we'll get a relation between V0 and Vx. First, I'll write the equation like this. V0 by 4, I wrote it as 3 V0 by 12. V0 by 12 is still there. 2 V0, I wrote it as 24 V0 by 12. Minus V0 will become plus V0. I wrote it as 12 V0 by 12. Minus Vx, I wrote it as minus 12 Vx divided by 12. I did this so I have the same denominator for all of them. Now I can cancel the denominator. That gives me 3 V0 plus V0 plus 24 V0 plus 12 V0 is equal to 12 Vx. So V0 is 12 by 40 Vx or 0.3 Vx. Again, Ix is the current that flows through the 1 ohm resistor in this direction. 1 ohm resistor has Vx potential here and V0 here. Current is flowing in this direction. So current will be Vx minus V0 divided by 1. But V0 is 0.3 Vx. So we get Ix is Vx minus 0.3 Vx or 0.7 Vx. From here we get Vx by Ix, it is 1 by 0.7 ohm. We can also find the Thevenin voltage by keeping these two nodes open and finding whatever is the potential we get across these 2 points. But as I said before, we are using Thevenin's theorem to find the input and output impedance of the amplifiers. So the voltage part does not matter to us right now. This much is enough. Let us see how we can measure the input impedance and output impedance of a BJT amplifier using Thevenin's theorem. For that, I have taken the basic idea of an amplifier that we developed before. The idea is this: we need a current source that provides a current I which will be proportional to the voltage that we apply over here. I here will be a constant multiplied by V1, V1 being the voltage that we give over here. So the first question is answered. We do have a dependent source in this. So we have to apply the second method. Let us try input impedance first, which means we have to find out the impedance between these 2 points. So we have to connect Vx between these 2 points and find out what will be Ix. Now, if you find Vx by Ix, that will give you the input impedance. Let's see how to find the output impedance. This is the circuit. The first rule the first rule is to turn off all the independent sources. Do we have an independent source? Yes. V input over here is an independent source. To switch it off, we have to short it. Now, we need to find the Thevenin resistance across these 2 points. That means we have to apply Vx between these 2 points and find out what is Ix. Now, if you find Vx by Ix, you will get the input impedance. Let us solve a problem. We have to determine the input impedance of the circuit if the transistor is operating in active region. Well, this is a very simple circuit. We have applied VCC to the collector. Input is given at the base. To find the input impedance, first let us draw the small signal model of this circuit. It will look like this. I have also included early effect to show that there is a resistor R0 between the collector and emitter. We have to find the input impedance, which means the impedance between base and emitter. So I have to connect Vx between these 2 points and find out Ix. This is actually pretty simple because you can see Vx is directly connected across the resistor R pi. And Ix is the current that will flow through it. So using Ohm's law, we can write Vx is going to be Ix R pi. Or Vx by Ix is going to be R pi. But Vx by Ix is the input impedance. So we can say input impedance is simply R pi. Now another important thing we can see here is this. We know R pi is given as beta by Gm. But Gm is Ic by V pi. So we get R pi is beta V pi by Ic. Beta is the intrinsic current gain of the transistor, Ic is the collector current. So we can say a higher beta or a lower Ic can result in a higher input impedance, which is desirable. Let us see the next question. Determine the output impedance of the circuit if the transistor is operating in active region. This is the exact same circuit. So let us take the small signal model again. I have still included R0 to show early effect. Here input is at base. So in the small signal model, we have to connect it between the base and emitter like this. But the first rule to find the Thevenin resistance is to turn off all the independent sources. Here input voltage is an independent source. We have to turn it off, which means we have to short it like this. What we have to find out is the output impedance, that is the impedance seen at the collector. So we have to connect Vx over here and find its relation with Ix. The first thing I can see is this. R pi is shorted. Whatever potential it has over here is exactly what it has over here. So V pi is going to be 0. If V pi is 0, Gm V pi also becomes 0. So technically, no current is flowing in this direction. That means all of Ix will flow through R0. According to R0, it has a potential Vx across it. and has a current Ix flowing through it. So using Ohm's law, we can write Vx by Ix is R naught. But Vx by Ix is our output impedance. So the output impedance is R naught. This is the impedance you see when you look through the collector. Let us do something here that we have already done before. Let us assume the potential at the lowest point here is 0. That means the potential at all these points is equal to 0. We can consider it as our ground. We can define every other potential with respect to that. For example, if this point has 0 potential, then I can easily say this point has Vx potential. Why? Because the potential difference between these 2 points is supposed to be Vx. So in this particular circuit, the emitter is at 0 potential, base is also at 0 potential. We can say the emitter and base are grounded. If we apply this idea, we can say R naught is the impedance you see when you look through the collector when the emitter and base are grounded. Similarly, in the previous circuit, we can say R pi is the impedance you see when you look through the base when emitter is grounded. Let us solve another problem. We have to determine the impedance that is seen at the emitter of the circuit if the transistor is operating in active region. It is given that the early voltage is infinite, which means we can ignore the early effect. The input has to be connected at the base. Now we have to find out the impedance that is seen at the emitter. So Vx will have to be connected at the emitter like this. That creates an important problem. The ground will not be over here anymore, it is over here. So the input cannot be connected like this. Input is connected at the base. It should be between the base and the ground. So we have to connect it like this. Since early effect is to be ignored, we do not have R naught over here. Also, since this is small signal model, VCC will not be included. Collector will be directly grounded. It can be shown over here like this. One more thing before we do the analysis. We have a resistor R pi over here. It has a potential V pi across it. So the current that flows through it will be V pi by R pi. Also positive potential is here, negative potential is here. So this current is going to flow in this direction. Let us show it. A current V pi by R pi flows in this direction. The first thing that we have to do before we find Thevenin's resistance is to turn off all the independent sources. We have V input, which is an independent source. So to turn it off, we have to short it. Now, let us apply KVL across the left loop, that is over here. I'll start from this point and go clockwise. As I go, I can see V pi from positive to negative. Let me write it down. Further as I go on, I can see Vx that is also from positive to negative. So I will write plus Vx. In the left loop, these are the only two voltages I have. So according to Kirchhoff's voltage law, the sum should be equal to 0. This gives me V pi is equal to minus Vx. Now let us apply KCL at the emitter node. What are the currents we have? We have V pi by R pi that is coming into the node. We have Ix that is coming into the node. We also have GM V pi that is coming into the node. The total sum has to be equal to 0. So we can write like this. V pi by R pi plus GM V pi plus Ix is equal to 0. But we have already seen V pi is minus Vx. So let us replace all the V pi's over here with minus Vx. That gives us minus Vx by R pi minus GM Vx plus Ix equal to 0. So we get Vx multiplied by 1 by R pi plus GM is equal to Ix, or Vx by Ix is 1 by Gm plus 1 by R pi. Before we call this the impedance, let us do a tiny bit of approximation. We know R pi is beta by Gm. Beta is the current gain and it is usually between 50 to 200. If we take the average, we get 125. So R pi is beta times 1 by Gm. On an average, it is 125 times 1 by Gm, which means R pi is very much larger than 1 by Gm. Or we can write 1 by R pi is very much smaller than Gm. So when we take Gm plus 1 by R pi, since 1 by R pi is very small when compared with Gm, we can approximate this to just Gm. That gives us Vx by Ix is approximately equal to just 1 by Gm. So the impedance that we see when we look through the emitter is 1 by Gm. Using this idea, we can model this circuit like this. You can see that Vx in the circuit is connected between the emitter and the ground. But here the collector is also grounded. So we can say Vx is connected between the collector and the emitter. In the circuit model, we can show it like this. When Vx is connected between the emitter and collector, the impedance of the circuit seen will be equal to 1 by Gm. Let us conclude what we learned. The impedance seen at the base of the transistor when the emitter is grounded is R pi. Impedance seen at the collector when the emitter is grounded is R naught. Also, impedance seen at the emitter when the base is grounded and the early effect is ignored is 1 by Gm. Now, naturally, there will be a question. Why are we ignoring early effect only in this case? In both other cases, we took R naught. Well, the reason is simple. In the third case, the analysis will become difficult if you include early effect. But that is only for the normal people. We are the smart people, we are the nerds. We should be able to do it, right? Let us do it. Let's determine the impedance that is seen at the emitter of the circuit if the transistor is operating in active region. Early effect is to be included because early voltage is less than infinity. In that case, a small signal model will look like this. The only difference is we have connected R naught to show the early effect between the collector and emitter. Let us see how this makes the analysis difficult. Remember, we applied KCL at the emitter load. Earlier, these were the currents we had to take into consideration. V pi by R pi in this direction, Ix in this direction, and Gm V pi in this direction. But right now, we'll have one more current that is coming from R naught. So we'll have to find out what is that current. R naught is connected between the collector and the emitter. So the potential across it is VCE. That means current through it will be VCE divided by R naught. The only problem is we do not know what is VCE. Then how will we do the analysis? Watch carefully. I am going to teach you a smart way to do this. Earlier, when we did not consider early effect, our small signal model looked like this. There is no R naught. After finding the Thevenin resistance, we drew an equivalent circuit like this. We said that when Vx is connected between the emitter and collector, the circuit behaves as if it has a resistance 1 by Gm across emitter and collector. Now, the new small signal model looks like this. The only difference is there is an extra resistance R naught between the collector and the emitter. So, to draw its equivalent circuit, all we have to do is take the previous equivalent circuit, connect an extra resistance R naught between its emitter and collector, right? Let's do it. So this will be our equivalent circuit model when we also consider early effect. R naught and 1 by Gm are in parallel. So the equivalent resistance between the emitter and collector at this point is R naught parallel to 1 by Gm. We can write Vx by Ix is 1 by Gm parallel to R naught. Thevenin resistance across those two nodes is 1 by Gm parallel to R naught. Or that the impedance seen when you look through the emitter at this circuit is 1 by Gm parallel to R naught if early effect is also included. Remember this method, we are definitely going to use it in the future. So that's all about it for today. See you in the next video. And don't forget to subscribe.